Yeah, most of them are from your class. But there are also one or two from the data science
Okay.
and and also somebody from physics and computer science and one
Physics and
person from
computer science
huh?
from CMI.
Yeah, BSc physics and computer science. You are in maths and computer science, right?
Yes, physics and maths. Maybe. Yeah.
Yeah, physics and computer science also there are I think one or two students. Then one student from MSc maths, I think.
Oh.
So your class constitutes the majority. Mm, so I will try to send.
Okay.
See, the thing is, if you look at the participants list, that is accessible to you, right?
Yes, that is.
Participants list, I think now has 19 or 20.
Okay.
Okay. And one thing I can easily, for you to eliminate certain things, are that all the people who have opted for SP2 have done SP1 last semester. Okay. I mean, I was wondering, I also found some names who were not part of SP1 last semester. Then I thought probably some of them might have done SP1 in an earlier year. So, so that by that itself, you can eliminate quite a few.
Okay, got it. Okay, thank you, sir.
So that might give you just yeah, this thing of about maybe 14 or 15. So you are so
Okay, got
easier to I don't know this. I mean, I don't know.
it. Okay, got it.
Yeah, I think. Okay, I will try.
That is it. Got it.
But last semester, did you have that thing? Last semester there were 38 or 39 students.
Yes,
Yes.
last semester there was.
Yeah, we one was a fairly large batch, and then
Yes.
the participants list listed initially about 70, and then later on it came down to 60 or something.
Oh, wow. Okay.
So anyway, this time it will be okay. I think let us get started. I will share the screen. So Soumya Agarwal has not come so far. Okay, sometimes he comes late. Yeah. So today we will start looking at non-homogeneous Poisson processes. So straight away we'll go to the definition. So NT is a continuous time stochastic process. And at zero, it is identically zero. And the process NT has independent increments. So T1 to T2 and T3 to T4 are two independent time intervals. Then the NT1 minus NT2 minus NT1 and NT4 minus NT3 are independent random variables. So it's a counting process with independent increments. So in other words, what we had given as the postulates for the homogeneous process, N1 to N3, these are satisfied. N1 to N3 are satisfied also for a non-homogeneous Poisson process. So basically, whenever one says Poisson process, these are the basic characteristics: independent increments and counting process. So, and of course, with one more condition that the increments should be Poisson distributed. Yeah, please note it down if you want to. Anyway, this is. And for any S less than T, time points, the random variable nt minus ns as a Poisson distribution with parameter integral s to t lambda r dr, where this lambda is the function now. So this is a Borel measurable non-negative function, a nice positive function. Having main thing is finite integral over every bounded set or bounded interval. So one makes this kind of a assumption, Borel measurable, which is a very, very minor assumption, so that this integral makes sense. So since you have done measure theory, you will be knowing that. In principle, it would be a piecewise continuous function or continuous function. I mean, in practice, many cases. Consequently, this integral is non-negative. It makes sense. It is non-negative and finite for every finite interval, St. So, of course, if even in the time homogeneous case, you know that if you make this as the third assumption, apart from n1 to n3, if you make this assumption, that gives you all the postulates of Poisson process. So the rare events, that is, two or more events cannot occur simultaneously and things like that, all those things will follow from here. Of course, N4 is not included here at all. N4 is the stationary increments. That was possible because in that case, that this function lambda r was a constant lambda. So if these things happen, then the process NT is called a non-homogeneous Poisson process with rate function lambda or intensity function lambda. In the homogeneous case, we said it was a Poisson process, homogeneous Poisson process with arrival rate lambda. So this is the rate function. And there, the object corresponding to this integral was lambda times t minus s. Okay. If this lambda is a constant, I mean, this function lambda is a constant lambda, then NT is our good old time homogeneous Poisson process with arrival rate lambda. So the example 2, which considered that is a in Poisson process 3, the second example, verify that the N1T and the N2T are non-homogeneous Poisson process. Of course, the independent increments property, etc., will follow by some of the kind of arguments we'll be giving soon. And you can check the N1T that has a rate function that there was a constant lambda which arises from that original process N, its rate multiplied with 1 minus GT. And N2, it is lambda times GT. Under fairly general conditions, a non-homogeneous Poisson process can be transformed to a time homogeneous Poisson process. by a so-called here time change. So somehow something give it as a problem. Basically, whenever this kind of this function has an inverse, so that kind of a thing is possible generally. See, this is lambda is non-negative function, and therefore this will be non-decreasing. If you consider this function 0 to t as a function of t, that would be non-decreasing. So if that is sort of invertible, then what we say here will be possible. So the rate function, if it should not be sort of 0 on or in a interval, sub-interval, then that kind of an inverse will not be possible. Generally, without that kind of a thing, this can be transformed to a homogeneous Poisson process. So studying a non-homogeneous Poisson process per se is not that difficult, or rather, all the basic difficulties are here, time homogeneous Poisson process. But this kind of a thing also is very, very useful and also will come up because, as you have seen in that example 2 of that earlier notes, starting from a phenomenon which has for time homogeneous Poisson process, we sort of coined two processes, stochastic processes, N1T and N2T, which are not homogeneous Poisson processes. Soon we will see another case, that is what we will be seeing next, more or less, of a non-homogeneous Poisson process arising from a homogeneous case. So please note it down. Okay. So this is an example from queuing theory. Queuing theory itself is a very vast subject. Actually, queuing theory is a subject which is just about 100 years old. This arose out of telecommunication systems. So it is purely owes its origin to engineering sciences. So we will just look at one snippet or one example from there. So as the name queuing theory suggests, this thing concerns customers arriving at some service station. This could be a railway booking counter or even airlines booking counter, or passengers coming to board a train or a bus or a plane at a station, or it could be telephone calls coming into a telephone exchange. So there, the calls, each call is a customer. And service means that it has to be connected to perhaps whatever it wants to see. Say, for example, you are doing something on the net, you would like to be connected to the internet or to the particular, let's say, website. So the time you have to wait and things like that. So that the service provider has to give you connection. So in such cases, the number of customers arriving can be huge. So this is an ideal assumption one makes here. Upon arrival, the customer is immediately taken up for service, which means there is no shortage of servers. This is the assumption. If this can be assumed if generally the customers arriving, that is the traffic, is rather low compared to the number of available servers. So the service times, so that is the customer after arriving and also immediately he is taken up for service, how long it takes for the service to be completed. Maybe if you go there to your station to book the ticket, how long after you reach the head of the counter, how long does it take to book the ticket? Or at a petrol bunk, how long it takes for the thing to be filled. So the service times are assumed to be independent IID random variables with a common distribution function G. So we assume this distribution function because the random variable constant can be discrete or continuous. Okay. So these service times random variables are also assumed to be independent of this process, as we had done earlier. So we have two, let's say, objects here, NT denoting the number of customers who arrived during the time interval 0 to T for every T. And GY is the probability that the service time is less than or equal to Y for every Y non-negative. So the random variables NT and the service times which have this common distribution function, these are two independent families of random variables. And also in addition, the service times are IIDs. So now let MT denote the number of customers who have been served during 0 to T. Of course, from among those who arrived during this interval. So it is a well-defined process. So one wants to show that this MT, this new process, is a non-homogeneous Poisson process. See, because of the nature of assumptions here, that there is no shortage of servers. So that is every arriving customer is immediately taken up for service. A customer who joined later can finish his service before a person who came earlier. So because of this assumption, there is nothing like the first come, first serve, because there is no shortage of servers. Okay. Yeah. So a person coming later can leave the system much earlier than a person who came earlier. Please note it down if you want to. So we want to show that this has independent increments. Yeah, this property. So the MT has independent increments is something which we have to show. So this should be T1. Please make the correction. T1, T2, T3, T4 be in that order. T3 and T2 can be the same. They can be equal. So make this correction. This should be T1. So we denote by M1, MT2 MT2 minus MT1. So this is the number of customers whose service was completed during T1 to T2. The service would have started at times whenever they had arrived. So it is completed during T1 to T2. Because MT is the number of customers who have been served during this. And similarly, defined by M2, MT4 minus MT3. So those whose service was completed during T3 to T4. So one needs to show that these two guys, M1 and M2, are independent Poisson random. Note it down. So for ease of reference or writing, we are going to say that all the M1 guys are of type 1 and all the M2 guys are type 2. So declare a customer to be of type 1 if his service is completed during T1 to T2. And similarly, the customer is of type 2 if his service gets completed during T3 to T4. Now, denote by M3 NT4 minus M1 plus M2. These are called customers of type 3. What does it basically mean? This means M3 customers are all those who have arrived during 0 to T4, during the interval 0 to T4, but who are not of type 1 or type 2. That is, people whose service is still not completed by time T4, or those whose service was completed during T2 to T3. T2 can be strictly less than T3. Those who left the system during that time gap are also included in M3. So keep this type 1 and type 2. The thing is that T2 to T3 is those who leave during T2 to T3 is also are of type 3. So that is why one says that those who arrived during 0 to T4, but not of these two types, because it doesn't mean that M3 customers are still waiting at time T4 for the service to be completed. It also includes all those whose service was completed during 0 to T1 also. However, it's clear that all these M1, M2, M3 are non-negative integer valued random. And clearly M1 plus M2 plus M3 is NT4. That is the totality of all customers who arrived during 0 to T4. Okay, please note it down. So for non-negative integers K1 and K2, so we want to prove that M1 and M2 are independent and so on. So we consider probability M1 equal to K1 and M2 equal to K2. So that is same thing as probability M1 equal to K1, M2 equal to K2, and M3 equal to K3, and K3 running from 0 to infinity. I mean, K3 can be much larger than K1 or K2. I mean, we cannot easily give a bound on that, okay? Of course, it will be finite. For almost every trajectory, it will be finite. But it can be huge because our thing is T1 less than T2 less than or equal to T3 less than T4. So the T2 to T3 can even be a very, very large interval compared to T1, T2 or T3, T4. Okay, now this probability one can compute since M1 plus M2 plus M3 is the totality of all the customers who came during 0 to T4. That is, it is given NT4 equal to K1 plus K2 plus K3. So this conditional probability multiplied with probability NT4 equal to this. And of course, probability NT4 equal to K1 plus K2 plus K3, we know because N is a homogeneous process. Note it down. All right. So now we need to compute this first. And for that, we have a handle on that. because of the connection between homogeneous Poisson process and the order statistics involving uniformly distributed random variables. So we will use that. So for any integer n, let u1, u2, un denote IID random variables, each having a uniform distribution 0 to over 0 to T4. Of course, as we had seen in the earlier discussion, these UIs can be taken to be independent of this stochastic process NT, as well as the random variables which gives the service time. The IID service time random variable. So now we take n equal to k1 plus k2 plus k3. And then use the theorem which gives the connection between the homogeneous Poisson process and the order statistics involving uniform random variables. So then, please be very careful in writing this. Probability M1 equal to K1, M2 equal to K2, M3 equal to K3, given NT4 equal to K1 plus K2 plus K3. So in terms of these types which we have temporarily defined, among these, the total number of K1 plus K2 plus K3 customers who arrived during 0 to T4, exactly K1 are of type 1, K2 are of type 2, K3 of type 3. So that probability given NT4 equal to this total. Since this order statistics UI, random variables UI are independent of the process N, therefore the order statistics will also be independent. Consequently, this probability, as you have seen in that theorem 1, is this. Say all those customers, let us say, who arrived during these things, let's say they are arranged according to the time of arrival. U1 denotes the class of customers who arrived who are the first, and so on. So U sub bracket 1, U sub bracket 2, and U sub bracket K1 plus K2 plus K3, exactly Ki are of type 1, type I, etc. I equal to 1, 2, 3. This 1, 2, 3 is not visible. But since this is the statement concerning the order statistics which involves all the UIs up to K1 plus K2 plus K3, this event is same thing as among U1, U2, this thing, exactly Ki are of type. You can do such things when it involves all the random variables, like if you are going to sum over all the random variables. That's what we did in the earlier instance. Here we are saying some statement which is applies to the totality of all these guys. So probability, so this probability is same thing as among U1, U2, Uk plus K1 plus K2 plus K3, exactly Ki are of type Y. I running over 1, 2, 3. So this is the trinomial thing. So from K1, K2, K3, you choose K1 of type 1, K2 of type 2, K3 of type 3. So that can be done in this many ways. K1 plus K2 plus K3 factorial divided by K1 factorial, K2 factorial, K3 factorial. Times a typical event of that nature, that is probability of the first K1 of these guys in this way of indexing are of type 1, the next K2 are of type 2, and the last K3 are of type 3. Of course, it is quite possible that a person who came first might be of type 3, namely his service might have been completed before T1 or between T2 and T3, or even might not have been completed by T4. And it is possible that a person who came last might already be leaving. So this we can write the second quantity here. I mean, that is a probability U1 to UK1 of type 1, UK1 plus 1 up to UK1 plus K2 of type 2, and the remaining of type 3 as P1 to the power K1. There are K1 involves K1 random variable, IAD random variables here, times P2 to the K2, P3 to the K3. So please carefully write. One can easily make a typographical mistake or a transcription mistake. If I were to write it on the board, I would have easily spent 10 minutes or 15 minutes checking that there is no error. So where little pi is probability that the U1 is of type I, because all the UIDs are random variables, IIDs. So for I equal to 1, 2, 3. And P1 plus P2 plus P3 is obviously 1. We will stop here for the day because the computation of PI I want to do at one go, and I thought I wouldn't be able to complete it today. So if you want me to go back to any of these slides today, you can ask me right now. Okay, otherwise I will stop sharing. By the way, this did you get both the announcements that I sent yesterday?
The mail and the Moodle message, you mean?
Yeah, one thing from
Yes.
the Moodle thing, which I sent it before I looked at Professor Manoj Kumni's email. I had wanted an alias to be created
Right.
so that the question papers, etc., can be sent so that all the students receive at the same time. So that
Yes, I
saw.
got both.
Yeah, okay. Good. I just wanted to. I have to report to Manoj that things have been delivered using that.
Okay.
alias. So next class we will take it up, and okay, let's hope that all those who don't come at least see the notes. Now, I do find that the people who have looked at the number of people who have looked at the slides, the proportion is much better than what it was last semester. So that's a. But is the connectivity so bad? Why is it that? I mean, what about this kind of attendance thing in other classes?
I think it has been low in other classes also.
That's what
Typically, if
I would think,
recording has been going.
why?
That I'm not too certain. Maybe 10:30 is slightly too early in the morning.
But then what about the afternoon classes?
That's also equally bad, maybe I would say. Not
Those
sure.
who are now who cannot come, it is too late for them.
Yeah.
Because I thought most of your classmates living in a reasonably big place where internet connectivity is there, right?
Yes, I would assume so, but yeah, not entirely certain,
Yeah.
but I could assume so.
So that is anyway puzzling, because I thought it is always better to attend the class so that if there are, for example, there are more number of students attending, like a classroom, then somebody might ask some question. So consequently, others also might get attentive. And invariably, when a teacher makes a mistake, and if a student catches it in the class, so that particular thing, even the other students will remember for a long time.
That's correct.
So that kind of, and one student may ask one question, and that may provoke somebody else to ask another question. So that kind of, those are those kind of, I would say, advantages are lost.
Yeah, that's
And some teachers, I understand, they give special weightage for attendance. I somehow don't believe in that, especially all the students are mature. They don't need such incentive. And especially for an optional course. Okay, anyway, they may have their own reasons. Who are we to question? Okay, I will end the session now, and Wednesday we will. Yeah, thanks.
okay. Have a good day. Bye.
Take care.